Talk about the following question. So let's say we have a star algebra, which for people, I know some people know algebras and all the things I'm going to talk about pretty well, but for people who don't, let me just say what it is. It's a vector space over C with multiplication, which is a bilinear map, which is associative, and a star operation, which goes from A to A, such that AB star equals B star A star. And the question I want to talk about is when you're given a star algebra, how do you know if an element in that star algebra is positive? And of course, I need to define, if I'm going to define what a star algebra is, I better define what positive is as well. So let me first, give an example of what we're trying to capture. So B of H is a star algebra for any Hilbert space H, and we say that T in B of H is positive if V star T, V is greater than or equal to 0 for all T in H, or equivalently, if T is equal to S star S, some S in B of H. Okay. And hopefully that's a familiar definition. Maybe a comment on positive. Really, if you're used to matrices, that would be positive semi-definite. Okay, so greater than or equal to 0, rather than strictly positive. Looking at these two definitions, one thing to note is that it kind of so in matrices, both of these are practical criteria, more or less. In Hilbert spaces, they may not be, but the spirit of them is that from this one, right, we can prove that T is positive by giving S. So that may not be practical in a Hilbert space, depending on what T is. But if we do know that T is of this form, then we know that it is positive. And this one is related to showing that T is not positive, because if we can show T not positive if by finding so V with V star T V strictly less than 0, right? So the two very familiar definitions are kind of related to these two tasks for positivity, which we would need to solve if we want to be able to decide if something is positive, be able to tell when it's positive and tell when it's not positive. Okay. So now back to the general case, what does it mean for an element in a star algebra to be positive? Well, there's two possible definitions we could give. Okay, so one is that, so we'll call this one, we'll say that A is sum of squares, or SOS for short, okay? If there are B1, BK in A, with A equal to the sum over BI star, BI, okay? So this one generalizes the second definition here. And we say that A is representation positive, or for this talk I'll just say positive, if so phi A is positive for all phi from A to B of H. Okay, so for all representations. the idea is we have, so representation is just a star homomorphism. It's a linear map which preserves the multiplication in star. And we look at all possible ways of thinking about our star algebra inside or kind of mapping to operators in a Hilbert space, and we ask that A be positive in all those representations of our star algebra. And if that's true, we say that A is positive. So, and again, these are kind of related to two ways that we might be able to kind of address the question of, deciding whether A is positive, right? If we, for being SOS, we can show that something is SOS by actually finding a sum of squares, and we can show that something is not positive by finding a representation and then a vector in that representation such that V star phi, so not positive. The V star phi A V less than 0 for some phi and V. And that may not be a practical problem depending on what our spaces are. Now, why do we care about positivity? Well, here's one possible reason. So we could define the operator norm to be the supremum across all star representations of the operator norm of phi A, okay? Which, so that turns out to be the infimum over lambda such that lambda times identity minus A star A is positive. And as stated, this could also be the infinity, so I'll add that in case this set is empty. So we can see that if we know that lambda minus A star A is positive, then that implies that we have an upper bound on the operator norm of A, so less than lambda, and if it's not positive, then we get a lower bound.
So this is
lambda squared.
square norm, right?
Square.
Oh,
the same
yes.
comments.
Yeah, thank you. Okay, it's kind of annoying. Square there, and then I guess we just put that everywhere. Yeah.
Can I ask another question, William?
Yeah.
Star algebras, abstract star algebras are hard to understand if you're not a C-star person. What happens if you take the convolution algebra on L1R? That is the star algebra.
Well, I was happy with your first statement, but I'm not sure how to answer the.
I just want to know whether for that thingy positivity is what you think it is.
Let's talk about that after, because I don't have an answer ready to go.
Okay.
So, yeah. But if you have a more familiar example.
It's just that we have little intuition when something is not a C-star algebra.
Yeah, I agree. But actually, so although I added an infinity here, I plan to only look at what are called Archimedean examples, where this operator norm is bounded, and everything completes to a C-star algebra. So, yeah. You can think about examples we're going to look at. There will be subsets of C-star algebras.
But so just to ask one more, but you insist on the representations into bounded operators all the time?
Here?
Or just over there?
Oh yeah, here.
So for example, if there are no such non-zero maps?
Yeah, exactly. So in some star algebras, this would be a pretty useless definition. It wouldn't be a good definition of positive, yeah. Okay. So as an example of using this, let's look at this algebra. Take the group algebra of Zm, free product with itself n times, and then take the tensor product with itself. Okay. So here, this algebra, if just one copy, is maybe more pleasantly presented as the star algebra generated by PXAs, where x is between 1 and n, and a is between 1 and m, okay, with the relations that pxa squared equals pxa equals pxa star, and sum over pxa's is equal to 1. So when we look at this tensor product, what we're really saying is that this is the same thing, but with not just pxa's, but also qyb's. So it's the same relations on everything for both the p's and the q's, okay? But also then the p, xa, and qyb commute. So the p's correspond to the generators of the first factor, let's say, and the q's for the second factor. So if G is a non-local game, I'll rely on Wernstock maybe to say what that is. Probability distribution, let's say pi, and winning predicate v. So we can define the game functional, b phi g, so the sum over phi xy, vab xy, exa dyb, would be sum over xy, a, and b. And then this, okay, so this works for, let's say, a game with m being the number of answers and q being the number of questions. We can write down this functional. And then when we look at the value of this game, particularly the commuting operator value, okay, we get that that's equal to the operator norm of phi g. So this is just one example where we might want to be able to calculate operator norms, and if we could answer positivity, we would be able to do that. But it's a theory that kind of applies in many areas. Probably some people in the audience are familiar with other areas in quantum information, where you can use the same ideas, and lots of other things as well. But I would say for people who are interested in games, the particular question is just, can you answer positivity in this algebra? That's the algebra we'd really like to know about, and it's because it kind of represents, it's the algebra for measurements made on two different sites. So if we want to understand correlations, so-called, or behaviors that can happen between two different locations, and this is the algebra to look at. So back to what happens in general. So there's a kind of a positive Stellensatz. And so if A is Archimedean, meaning that the operator norm of A is bounded for all A and A. Okay, so sometimes it's called a semi-free C-star algebra because you can make any Archimedean C-star algebra into a C-star algebra. Then we have that this is the highest that goes. Move this up to right and then I'll move it back down again. So what we have is that A is positive in this representation sense here, if and only if A plus epsilon times the identity is a sum of squares for all epsilon greater than 0. Which means that if we look at this operator norm, it's not just the infimum over, so rather than taking the infimum over lambda there, I could also just take the infimum over lambda plus a little epsilon, which would be a sum of squares. So that turns into the infimum over lambda, such that lambda minus a star a is a sum of squares. And that's great because I can actually, you actually can turn this into a procedure for upper bounding the operator norm. You search over sums of squares for things of the form lambda minus a star a, and whenever you find one, you know you have an upper bound. Like, you don't have a practical way of proving things are positive in general, but you can show things are sums of squares, and whenever you find one, you've got an upper bound. And then this is, so if you dualize that idea, it becomes a lot more practical to implement, and this is where kind of the NPA hierarchy and related ideas come from. Maybe that's misrepresenting the history of it a little bit, in the sense that I think, well, yeah, but they're very closely connected, these two methods for trying to upper bound the operator. Notice though, this result, this positive Selensatz, it's the most practical way we have of trying to compute, say, a gain value, but it doesn't actually help us decide the positivity question, either direction. Okay, so if you can show that A is a sum of squares, being a sum of squares will imply that you're positive in every representation. So if you can find it, that gives you an affirmative answer. But this theorem doesn't say that you'll ever be able to take epsilon equals 0 here necessarily. So something can be positive without you being able to find a sum of squares, as far as the theorem is concerned. And then it also doesn't give you a way to show something is not positive, right? So, and that's because you might think, well, if I can just find an epsilon such that this is not a sum of squares, then I know it's not positive. That's true, but how do you know that something's not a sum of squares? You've got a big star algebra, you've looked through a whole bunch of BIs, you haven't found it, but maybe you just haven't checked the right BIs yet, right? So, so it doesn't actually help us with the decision problem of whether something's positive at all.
Just once again for clarification, so does your definition of Archimedean exclude the fact that you have no maps into bounded operators?
Yes. What you mean is if something's Archimedean, then you have maps into bounded operators, yeah. Yeah. Oh, sorry.
I think you probably should assume it as well, right? Because otherwise...
So,
definition of Archimedean is a bit different, no? That you can show that there's a sum of squares for some number c minus a star times a.
yeah, you're right. So when I say it this way, I should take a boundary case. Let's figure out the right way to do it. Yeah. Yeah, I'm trying to cut a few corners on the exact details, but. So let's look at another example that's kind of helpful for figuring out if we can, that might be helpful for trying to figure out if we can decide this. So we can look at either the free group algebra or the just one factor here. Okay? So those are Archimedean. And for these, actually, we have that our definition of our two definitions of positivity are actually the same. So one is true if and only if 2. And actually this is if and only if 3, a third definition. Okay, so phi a is positive for all phi from A to matrices. Okay. So we have some terminology for these. Okay, so if one holds if and only if two, we say that this is Archimedean closed. And if two holds if and only if three, okay, so we say that A is RFD. So both these are both Archimedean closed and RFD, and this means that our kind of what we said about part two being a way to check that something isn't positive is actually a practical criteria, because it's kind of, you know, sometimes hard to work with Hilbert spaces, but we can write down all the maps to matrices, right? For this algebra, for instance, it's just collections of unitaries of order m, okay, inside matrices, and then for each one of those, we just check if the thing is positive, and if it's what this is saying is if it's not, eventually we will find we'll find some representation where it's not. On the other hand, one if and only if two tells us that there's a way in these algebras to show that something is positive always, because if it is positive, it's a sum of squares. So if you want to decide whether something is positive in this algebra, so we can decide if A and A is positive by combining 1 and 3. We search through all the possible ways of showing that it's a sum of squares, and we search through all the ways of all the representations to try and find a representation where this element is not positive, and eventually one or two of the others will be successful. Okay, so so whenever you have both 1 and 3 being equivalent to 2, then you have a decision procedure. It turns out for these algebras that's not the best way to do it. You can actually just use either 1 or 3 by themselves, because the results that prove this also give upper bounds on the size of the sum of squares that we need here, and also on the dimension of the matrices. So you can look through, let's say, all sums of squares of a certain degree, and if you don't find one, you know it's not positive. You just want to use 1, and similarly here you could look through all representations up to a certain dimension, and then if you haven't found that it's not positive by that point, you know it is positive. So that's not, combining 1 and 3 isn't the most practical way, but I think it's kind of, it's an interesting way to think about it, because we have these two definitions that kind of give us both sides of that decision problem, and when they agree, then we have a practical criteria. So this brings us back to our algebra here, and we can ask for this product algebra, is it also true that it is both Archimedean closed and RFD? If it is, we could decide. And this is where Hirschberg comes in. Okay, so back to our tensor product algebra here. So Hirschberg says that A is RFD if and only if Kahn embedding is true. Okay, and then of course we all know that means that MIP star equals RE. That's something to say about this. So what this theorem says, reinterpreted only, actually, am I reinterpreting it here? No, I'm going to give the literal statement of it. It says there's a map from Turing machines two non-local games. Let's say it goes from M to GM, so GM is the game associated to the Turing machine M, with the property that if M halts, then the finite norm of GM of the functional of GM is equal to 1, and here by the finite norm I mean the sup of phi A for phi map from A to MNC for overall n. Okay, so just going through finite dimensional representations. And if it doesn't halt, then we have that this norm is less than or equal to a half. We could rewrite this norm as squares back in. So as an infimum over lambda such that lambda minus phi a star A is positive for finite dimensional star representations. So if we think about what it means if A was RFD, let's see. So if A is RFD, it means whether being positive in, this would be for all finite dimensional star representations phi, okay? So if A is RFD, that means that this condition is equivalent to just lambda minus A star A being positive, which that would mean that this finite norm was the same as the norm we wrote down before, since we had the infimum in here. So that would tell us that so our finite norm of G of M is equal to our operator norm. And then if we think about our operator norm, we said we have a way of upper bounding it effectively by searching through sums of squares, or really if we wanted to do it actually effectively, using the dual and using the MPA hierarchy. And so if we are in the non-halting case, this is greater than or equal to half. We might not be able to find a proof that it's exactly equal to a half, but we can find that it's a half plus epsilon for any epsilon if we're in this case. There'll be a demonstration of that fact, which tells you that it's less than 1. Okay? So that would imply, using upper bounds, that we can prove that M does not halt when M happens to not halt. Okay, that we can prove that that's true, which is the thing you can't do for Turing machines, right? Because that would mean that we can solve the halting problem. Why is that? Well, we just do two things. We run the Turing machine M and wait for it to halt, and at the same time, while it's running, we go and calculate our upper bound. If we find an upper bound that's less than 1, we know it does not halt, and we can stop running the Turing machine. And then if it halts, we know it halts, and we stop computing the upper bounds. One of those two is guaranteed to finish, and we've computed the halting problem for that. So that can't happen. So A is not RFD.
Formally, wouldn't you also have to know that the map from Turing machines to games is sort of computable?
Yes. Yeah. So it is a computable mapping. Yeah.
Which is something C-star people often don't remember, right?
Good point. Yeah.
So this is a computable map, and
Yeah.
that's why I think that costs them a couple of pages extra.
Sure.
If you're
Yes.
really honest.
That's true. In fact, it's often not.
We don't understand that often. I mean,
Yeah. It's actually even not in mid-star equals RE paper. It's often something that is a pain point in anything about computability. That afterwards, at some point, there'll be some function that's just given, and then 10 pages later, you see a comment that's, and of course that map was computable. So, and you didn't read that. You didn't know to check for that the first time around. So you have to go back and reread the entire proof to verify. That happens a lot. Yeah, so it shouldn't be admitted as much as it often is, yeah. Okay, so the work I want to talk about is, so we've been kind of, in trying to understand this theorem and the landscape of it, the question is just, what else should we also look at? And looking at this picture, we wanted to know, well, it's not RFD. Is it also true that it's not Archimedean closed? Right? Do we have, if we had 1 equal to 3 equal to 2, we could decide the operator norm. We guess we probably can't do that because we can't do it for this finite norm. But let's just check that the 1 if and only if 2 breaks, or maybe it does hold, right? So, and what the point of doing that in the context of this MIP* equals RE theorem is to try and say, well, what does this theorem tell us about how we should approach that problem? Well, we should look for some computability way of trying to show that it's not true. So, so here's the theorem. With Arthur Mehta and Yuming Zhao, who's here and will speak tomorrow. So, so it says that if n is large enough, there's a map, there's a computable map from Turing machines to A, where same A, continuing with this A, okay, so product. Let's say it's M to alpha M, such that alpha M is positive if and only if M does not hold. It's an interesting point. So it's actually important here that this is into non-local games without any bound on the question and answers. Okay, so the question and answers here have to vary, whereas here this is for fixed n. So just as long as n is large enough. So actually, when we said here, I said that this implies that this is not RFD. It actually implies that there is some M and N where it's not RFD. They can't actually be RFD for all, but it doesn't. You have to do a little more work to get a specific, bound on M and N from that theorem. Yeah. so what we get as a corollary immediately is that if n is large enough, then A is not Archimedean closed. The reason is it's the direction of this that matters. Alpha m was positive if and only if this does not halt. So imagine that was Archimedean closed, right? You would have a way of, it would mean that if something's positive, it has a sum of squares decomposition. That's what Archimedean closed means. And so what we could do is, again, run the Turing machine to see if it halts, and at the same time look for a sum of squares decomposition for alpha m, okay? And if we find one, then we know that m does not halt, right? Whereas if the Turing machine halts, we know that the Turing machine halts. So in either way, one of those two things will end, and we'll have decided the halting problem. So it can't happen. So therefore, it couldn't have been Archimedean closed. That's the conclusion.
So this means you're limiting the number of questions,
Yeah.
and you still solve quantum embedding.
Oh, and actually, I should say also for m equals 2. It doesn't. So the question is it a replacement for this? Not at all, actually. So it doesn't say anything about quantum embedding. It only says something about the Archimedean closed side. Yeah. And so actually, the part of the reason we might say, like, let's look at what's the difference between this and that. This looks a lot easier, or should, because there's a gap here. This is the gapped problem. So we have to actually decide if the norm is 1 or a half. Here we're not requiring a gap at all.
You cannot strictly separate anymore.
Yeah, so we should look at the gap problem. So here's the gap version. So this is the gap version of the problem, not of the theorem. Yeah. So so here our question is some element positive. So this is A greater than or equal to, let's say, a half times identity? Okay. Or is there phi and v with v star phi a, v equal to, let's say, minus a half? Okay. And this needs to be a promise problem, so promise that one of the two is the case. And so there's another conjecture that is kind of a natural extension of this idea, which is called MIP_co equals co-RE. So conjecture. What it says is that there should be a mapping like this into games, such that m. So we replace the finite norm here with the operator norm. Okay, but whether m halts or does not halt has to switch here. So it has to be, if m does not halt, then this has to be, the operator norm has to be 1, and if it does halt, then the operator norm is less than or equal to 1. That's where we get the, that's the co-RE part of this. It's the opposite of RE, okay? The complement of RE. And this co stands for a commuting operator, where we take the actual operator norm and define them. So there are two different co's there. It's a nice coincidence. Yeah. So, but what that amounts to is that this gap version is RE complete. Okay. RE complete means that it's both contains RE, okay, the halting problem, in other words, and is contained inside. It's no harder than the halting problem. So we should say that this is a subset of RE. Okay, and the reason for that is, imagine that you do need to decide this. There's no good way of looking through representations. But if A is greater than or equal to a half, it has a sum of squares decomposition. And as soon as you find a sum of squares decomposition for A, you don't know that it's greater than or equal to a half, but you do know it can't be in this case. So if you're promised that one of these two is the case, you know you're in this case. So there's a way of deciding one half of these two conditions. So that makes it as hard as the halting problem. Okay, no harder than the halting problem. Excuse me. Yeah. And then what the MIP co-equals co-RE conjecture is also that it's as hard as the halting problem as well. So that tells you actually this is kind of complementary. Like it's a lot easier to prove things without a gap, because what can happen is you need it to be, in the halting case, not positive. So you can make the eigenvalue here that is negative be like 1 over the halting time. Okay, you can have a very small negative eigenvalue, and that's a lot easier to construct than something with a gap. But on the other hand, you can't. The gap version can't. So this is saying that this problem is co-RE hard. Okay. So this does not imply this either. They're kind of complementary. You can't prove non-Archimedean closeness with the gap version of the problem. You can only do that with this co-RE hardness. Because if you think about it, imagine this went the other way. Alpha m is positive if and only if m does halt, right? Like in this case, in the positive case of this, you can find a sum of squares. So it doesn't contradict the fact that you can't find a sum of squares for some elements. So it's kind of interesting how the whole picture comes together. In fact, it leads to the following conjecture that we made, which is that the problem is a positive. So again, A being this product algebra is pi 0, 2 complete. Okay, so we actually, if this MIP co-equals co-RE conjecture is true, then this problem is both RE hard and co-RE hard. Okay, so it has to be kind of harder than both. So this can't be like the final word on how hard this problem is, if this conjecture is true. And so then the question is, what's the natural answer of what it could be? Finally, this positive Stellensatz that I mentioned before, which was that you're positive if and only if A plus epsilon is a sum of squares for all epsilon. Okay. This actually now has something to say about computability. It says that this problem is contained in pi 0, 2. It's a for all there exists. Okay, for all epsilon there exists a sum of squares. So that means that this is a pi 0, 2 problem. And so I guess the natural guess is that it's pi 0, 2 complete, as hard as it could possibly be. But we don't have any evidence for it aside from the two things that are mentioned here. Oh, I have 5 more minutes, I think, right? Yeah, okay. So I was going to say a little bit about why the theorem is true. So the idea is that for every Turing machine M, there is a star algebra A of M, okay, which is finitely presented. So it's got a finite number of generators and a finite number of relations. And a projection. So let's call it P0 in A of M, such that two things are true. One, if M halts, then there is, oh, okay, hold on a second. missed an important detail that I was going to tell you first. Okay, so apologies. We're in the wrong theorem. So. Theorem, I wanted to tell you so in addition to this, and in fact our proof of this theorem is based on the following. The problem is A in C zm star n tracially positive is co-every hard. So basically exactly the same theorem, but now we're looking at tracial positivity, which is now A is greater than or equal to 0 for all tracial states on A. Okay? So, and now A is just one copy. Okay? So this is, so the way we prove this result is we first just prove this, and then we kind of use the same ideas that Vern was talking about with synchronous values, synchronous games, to extend it to the tensor product. Okay? So the tracial result is then related to the all states on the tensor product there. Okay. So apologies, because that's the theorem I wanted to give you a very small, some of the ideas in was this theorem with the tracial state. So this explains what I'm about to say. If M holds and there is a tracial state on A of M, so tau, such that tau of P0 is greater than 0. And 2, if M does not halt, then for any, okay, I have to be so careful with how I say this. For any tracial state tau on A, meaning this algebra. Oh, and actually M is 2 through this. So yeah. Actually, we could just make this even be maybe the best in this context would just be, so let's say any tracial state on the generators of this algebra. Such that the sum over tau ri star ri is less than epsilon. Okay. Then tau E0 is less than Cm epsilon, where Cm is a constant that depends on the Turing machine M, but not on epsilon.
What is n? So is n moving or is n sufficiently big? What is n?
Yeah, so n is, it's not sufficiently big. It actually depends on the, it's actually a specific constant particular to our instruction. So, yeah, so sufficiently big would work too, because then you could just do nothing with the rest of the variables. Yep, so sufficiently big. So continued here. So what we do is then, and also I should say, this presentation of AM and CM. So what we do is we set alpha M equal to the sum over Ri star Ri minus P0 over Cm. So the idea is, if we're in the halting case, we take the tau from 1, okay, and we apply it to alpha m, right? And the point of being a state on the on AM is that Ri is 0 in AM. So tau on this is just 0, but it's positive on P0. So what we get is something negative here. So tau of alpha m is less than 0, so it implies that alpha m is not tracially positive. Okay. Now, the difficult part of trying to come up with a construction like this is to figure out what happens in the non-halting case. Okay, so now you want to show that this thing is tracially positive. So you might want to try and relate your traces that you might consider to traces on the algebra AM that you used in the construction here, right? But you can't guarantee that any trace in the variables is going to be 0 on the Ri's. It could, for instance, make it a little. It could go up a little bit on the Ri's in favor of going up a lot on P0 and then end up being negative, right? But what part 2 guarantees is that if m does not halt, let epsilon equal the sum over, and we're given and tau is a tracial state. Okay, let epsilon equal the sum over tau of Ri star Ri. Okay, so then, maybe I should have put in less than equal to here. I think that's okay. So then this holds by definition. Okay, so that tells us that this is tau P0 is less than or equal to Cm epsilon. And that tells us that tau of alpha m is greater than or equal to 0, right? Or at most Cm epsilon on P0, then subtracting this part can't outweigh this. So that's, if you want to do a construction like this, that's the thing you have to control, is really get something like part 2 with. So you should think about this condition as kind of like an approximate representation condition. It says that in approximate representations or approximate tracial states, this value can't be too large. So, yeah. And you just need to find a computable, you need to make this computable here. If you can do that, then you've got what you need. Yeah. Okay, I'll stop there.